One, she's supposed to be dead. Doctors don't know what to do. We have a rare form of a rare condition of her heart. It's on the wrong side of the chest, which caused one of her lungs to shrivel up. But because her heart is supersized, she has worked
It's nice.
I don't even have wisdom teeth. I wear glasses. And my vision's still better than hers.
I can imagine science fiction.
Oh my god, no, it was so making jokes about this art light in like 7th or 8th grade. I had to do a presentation on respiratory fossils. And I literally created a slide and just titled it My Defense of
Visual aid.
This is the next mini exam. I made a mistake on it. I accidentally put mini exam 4, but it's actually 6. So it says that. Oh.
Thank you.
Yep.
3 or less.
So y'all can work in small groups on this one. All right, the other mini exam 5 is due on Wednesday, right? So, okay, let's get going. So last class we were talking about double integrals, and specifically we were talking about these 2 type regions that we can have. So when we started double integrals, we had just integrating over a rectangle, right, on the ground. And then we went to type 1, where your x is bounded between 2 constants, your y is bounded between 2 functions of x. And then type 2, your y's are stuck between 2 constants, and your x's are bounded between 2 functions of y, right? And we did this example. I went back and looked. I think I set this one up. I don't know if we actually did the problem, but I'm going to go to the next example, all right? So we're going to finish up this section, and then hopefully we'll get through 12.3 as well today. So here's a really interesting problem. So I put here example 5, order might matter. So look at the double integral that's being presented to you. There's no word problem here. It's not like find the volume underneath this surface, blah, 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 right? So we just need to kind of see what we can do with this, right? So we're going to do the integral from 0 to 1, an integral from x to 1 of sine of y squared dy dx. So we have an inner integral and we have an outer integral. So let's start with the inner integral. All right, we need to find the antiderivative, right? The antiderivative of this, and then evaluate it at the 2 endpoints. So we go over here maybe, and we say, all right, let's just try this, right? We stare at it, and stare at it, and stare at it, and then we go to what, Symbolab or something, right? Or we go to Wolfram. I'll go to Wolfram.
I go to derivative calculator personally.
Derivative calculator?
Or integral calculator.
Yeah. Let me put it in here. Sine y squared dy. And let's see what this gives us here. The answer is square root of pi over 2 times capital S. That looks like a function. S of something. What's S? Oh, okay. S is the Frenzel S integral. What? Okay, so this is way beyond anything that we've seen before. And this is Wolfram telling you basically can't be done without probably series. We could do this with series. We could definitely do it with series, but it'd be an approximation, which is okay, but it seems like there's something amiss, right? There's something that just seems amiss here. So I say here order sometimes matters, right? We have an integral we can't do. So what I'm going to do is I'm going to use the limits of integration to reverse engineer the region, all right? So we're stuck, right? No, don't know what to do. So if we look at this, if we look at the limits of integration, the outer integral is x, right? The inner one's y. So the 0 to 1 is my restrictions on x, right? My x here is bounded between 0 and 1, and then my y value is bounded between two functions of x itself, and then just the constant 1 function, right? So this is what this is going to look like if I try and graph this region, right? My x's are between 0 and 1. My y values always have to be between, well, the smallest it can be is x. That's the diagonal, right? The identity function, yes? So this is y equals x, right? And then this right here is y equals 1. So do you all see the region? You'll see it? It's the region where your x values are between 0 and 1, but your y's have to be between these two. So we're talking about this region in here. This is a type 1, right? This is what we'd refer to as a type 1 region because your x's are between two constants, your y's between two functions of x, right? Can we convert this to a type 2 though? Could you look at this as your y's are stuck between two constants and your x's are stuck between two functions of y? Could we? Yeah? What would it be? As a type 2, y's between 0 and 1. Okay, that'll give us this range. And then your x values are stuck between these two, right? So what would the lower limit on the x value be? 0. And then y. So all you do is take this equation that was solved for y and solve it for x. But it's already solved for x, right? So we're looking at these as functions. See, these are functions of y now. Instead of over here, these were functions of x. See the difference? What does that gain? I mean, what do we gain from this, though? What does that allow us to do if we do a type 2? It reverses the order of integration, doesn't it? So let's take a look at that integral. Now we will go from 0 to 1 on the y. We will go from 0 to y on the x. We're still integrating sine y squared, but now it's d what? dx dy, right? And that makes a huge difference. Because if we take the antiderivative of the inside now with respect to x, we're treating this entire thing like a constant, aren't we? And that's integrable, right? We should be able to handle that. So let's continue. Are there any questions on what I've done? So this goes to the outer integral. Now the inner integral, the antiderivative of that is just itself, because it's a constant, times x, right? Because when you take the antiderivative of a constant with respect to x, you get the constant in front of x. And then I'm evaluating that from x equals 0 to x equals y. So I'm going from 0 to y, and then I'll have my dx on the outside of that.
Dy on the outside?
Dy, yeah, thank you, dy. Now we just plug in, replace x with y, replace x with 0, subtract, and let's see where we are. I'll leave this one. Yeah, that was the old one. Let me get rid of it, right? No, that was the new one. Sorry. Okay, that equals, okay, the outer integral we haven't done yet. Okay, the inner one. Well, let's just do it. If we replace the x with y, that becomes a y. If we replace x with 0, that all goes away, right? So all we have is this times y, which I'm going to write this way, y sine y squared, right? That's what's in there, and then dy. And that is just a u sub integral, right? See, the fact that that y appeared actually makes this problem very doable now. So I continue. If I make this my u sub, I get what, y squared, so then I'll have a 2. I'll have to scale everything by a half to kill off that 2. So I'm just going to go right to the antiderivative. The antiderivative of this should be negative 1/2 cosine of y squared. Come on, Robert. Evaluated, come on. Evaluated from y equals 0 to y equals 1. Let's see. Do you all agree with this antiderivative? Right, derivative of that, derivative cosine is negative sine, negative and negative kill off, become positive. So I'll have sine of that, and then derivative of that is 2y. Then the half kills off the 2, so we get that. Right? So I'm not showing that work. Now just plug in 1 and 0 for y. So negative 1/2 cosine of 1 squared is 1, and then minus negative 1/2 cosine of 0. And let's see, negative 1/2 cosine of 1. Cosine of 1 is not a number that we should know. And then cosine of 0 is 1. So that just becomes a minus 1/2 times 1. And then we'll subtract and add. Subtract, subtract, so add. This is our exact answer. Yes?
Is that answer and the answer on Wolfram alpha, are they the same?
Well, I didn't do a double integral, but let's do it. Let's go to Wolfram, and let's actually do a double integral on Wolfram. So to do a double integral, there, so you can see, I just hit this definite integral, and then right here inside of it, I hit the definite integral again. So let's do the original one. The original one was what, 0 to 1, and then it was x to 1, or x to 1? On the first one we did, right? And then it was sine of y squared. And then we tried to integrate with respect to y first, then x. Oops, then x. Let's see what Wolfram gives us. Well, it gave us an answer. It gave us 0.229849, which I'm going to guess is what we would get if we did this. Make sure you're in radian mode. I mean, it should be the same answer, right? It should be. Is that what you're asking? Yeah. So, but the way that Wolfram's doing it is it's probably using some, well, it's using the Frenzel function to do it. So, but we haven't never even learned what the Frenzel function is, so it's beyond the scope of this class, for sure. All right, so the order. Sometimes if you get an integral that you're like, crap, this integral looks bad, right? Sometimes the region you're looking at is both type 1 and type 2 at the same time, right? Like that region was type 1, or you could look at it as type 2. Fortunately for us, we're able then to switch it. If that would have been a type 1 region and we couldn't switch it to type 2, we'd be stuck, yeah.
It's kind of like solids of revolution where you got to look at it and make determinations. That's the way to do it.
Yeah, like with like shells in washers, like sometimes you do a washer, sometimes you do a shell. Yeah, exactly, you can make that analogy, yeah. Okay, next example. This was actually just what we did, just so you know. We found the volume of that solid right there. So that weird, the surface, sine of y squared looks like this, right? And we were looking above this region, and we were trying to figure out the volume below that surface. And so that's it, 0.229, whatever it was. All right, some properties of double integrals that we've actually already stated, but just so it's in the notes. If you have some region D, right? This is your region that you're integrating over. You can break it up into two separate regions, D1 and D2, and then you can just add those two double integrals together. I remember someone at that table asked about that, right? Was it, okay, yes, if you could break it up. Yeah, here's the actual note saying, yes, we can do that. All right, this next property, please put a star next to this. This is actually, I think it's a very intuitive idea. Like it's easy to understand, but it's extremely useful later. Like we're gonna use this property, and it extends into higher dimensions as well. So let's see what it says. It says, let me kind of explain it. I'm going to explain this in pictures. So let's say on the ground you have some region, okay, D, that's on the ground, right? And then we want to find the volume underneath the surface, right? The volume underneath the surface down to that domain, right? The surface on top has up to this point been kind of whatever, right? What this note says is that if the surface on top of this is just the flat plane that's 1 unit high, okay, so your function f of x, y is not doing anything, it's just flat and it's 1 unit high, then when you calculate the volume, imagine this shape up here, right? That's not a very good picture, but if I tell you that this side right here is 1, right, like this length is 1, then wouldn't the volume, the numeric value of the volume, wouldn't that be equivalent to the area of this? Right, because how would you get the volume of this shape? You take the area and you multiply it times how deep it is. And if the depth of it is 1, then that area times 1 will always be the same number, right? So numerically, the answer you get here will always be the area of the domain that you're integrating over. That means if you want to find the area of a surface, an area of a weird region on the ground, you can use a double integral to find that area. I'm going to do it in the next section, you'll see. All right, we're going to prove the area of a circle is pi r squared. It's going to be really simple to do. Okay, good. This has to be 1 though, right? This function has to be 1 for this to work. Anything else about the notation? No? Double integral over d of the function will equal double integral over the function 1. Anytime we see this, that's just the area of d. All right, these examples we're going to do I took straight from the textbook. I think your homework is to do number 23 and number 25. Well, there's more than that, but I'm going to do number 24 and number 28, just to kind of give you an idea of how some of these problems look when you get to them in the homework. All right, so what I accidentally did was cut off the instructions, which are to find the volume of the solid that is bounded by all of these curves and surfaces. Right, so basically all of this information creates this solid, and we want to find the volume of it. All right? All right, let's see if we can't wrap our heads around what this looks like. Z equals x squared plus y squared. So way back in chapter 10, we talked about quadratic surfaces, and we went through it, and I said you should just be able to recognize when you see an equation, recognize what it kind of looks like. We're at that point where we need that. So the way I think about it is our z value is just, if I cover up the y squared, it looks parabolic in one direction, and if I cover up this one, it's parabolic in the other direction as well, right? Just not, the 3 kind of scales it, kind of stretches it. So this, it almost looks like a bowl, except it's kind of like stretched out in one direction and like more narrow in the other. And it opens up, right? Like from the origin, it should go up. We should never get a negative z value out of this. Now, had this been a minus, that would change things. It would be like a hyperbola, like almost like a hyperbola. It would be in one direction, it would go down, the other direction would go up. So it'd be like that saddle that we looked at. So I have to have some familiarity with what this object looks like. So I realize this looks like a bowl, right? Roughly speaking, I've got some bowl shape like that, centered at the origin. And then, I don't know, I've got my axes here. I'm just trying to get an idea of what it looks like, right? Okay, and then I have x equals 0. What's x equals 0? Well, that's the YZ plane. Let's break out the good old three-dimensional space. I always get this wrong. There we go. No, I got this wrong. I always get this wrong. Jesus. Can't be that hard, right? There we go. So I've got my bowl coming up, right? My bowl. And then x equals 0. X equals 0 is this is our x-axis, right? So x equals 0 is the YZ plane. All right, so I've got my bowl, and then I've got this plane cutting it in half. And then what? Y equals 1. So that's over here. I've got another plane going this way, right? And then y equals x is the diagonal this way, like this. Cutting it, right? So right now I've got this bowl with 3 planes cutting through it, right? And then finally z equals 0, which is the ground, all right? We've got to figure out what the volume is of the object that is enclosed by all of those surfaces. So I think the best thing to do to start would be to try and figure out what the domain on the ground looks like. So if I look at just what D is on the ground, what do I have down there? I have x equals 0, right? This is x, this is y. So x equals 0 would be the y-axis. That was one of the planes cutting through, right? Then I have y equals 1. Let me label these. X equals 0, that's the blue one. Then I have y equals 1. Then I have y equals x. Those are those 3 planes, right? We had one this way, one right here, and then the diagonal. So if you look at what's on the ground, we've got this little region here, right? That's enclosed by those 3 planes. Now that comes up, right? It comes up like this. But when they come up, they're going to intersect our bowl, aren't they? So our bowl forms the top. The bowl forms the top of the solid, right? The XY plane, the ground, creates the bottom of the solid. Do y'all see that? No? Yes? Yes? So I think we can, I don't know, y'all feel comfortable with the idea that this is D right here? Right in there? Right? Yes?
Just said again about.
So over here, let's see, let's make this X, Y, and Z. Okay, if we draw that over here, it looks like, we have to be careful here. Let me do it with the colors. Our Y comes out, Y is 1, right? So the Y comes like this. And then we have the diagonal, which I did in green. Where the hell's my green? The diagonal comes out like this. And then the blue is like this. Do you see that over here? Yes? Okay, now remember, these come up, right? And when they come up, they cut through this. And so we're trying to find the volume of the solid that's kind of bounded by all of those. So I'm saying wherever these come up and hit this up here, you know, it's going to come up. It's kind of hard to say how it's going to look up here. This is why having the computer is so useful. I just didn't want to use a computer because you don't have that, you know, resource when you're trying to do the problem. So I'm looking at this, I'm saying, okay, I also have the, don't forget this part, Z is 0, right? Z is 0 makes this, the XY plane is like, this is the ground, right? So I want to know the volume of the solid, that's the bottom of it. and then you come up, and then wherever it intersects this piece, that surface is the top of it. Got it? So top is the paraboloid looking thing, the bottom is the ground, and then the domain, the actual type of shape we have on the ground is this triangle. Okay? That make that better? Okay. All right, so in looking at this, I think this looks really good as a type 1 region, right? My x's are between 0 and 1, right? This is 1. So I'm thinking type 1. My x's are between 0 and 1. My y's are between, well, my y's are between here and here, right? So between x and 1. Now, let's go ahead and do this right now. What is my z between? We haven't done this before, but this kind of gives us an idea of what our top and bottom of our solid is. So what's the bottom of our solid? 0. Okay, and what's the top of the solid?
X squared plus.
Yeah, it's this, right? It's this equation solved for z, which it's already solved for z, isn't it? So it's just that. So the formula, if you look back in the notes from last time, the formula we have is this one right here. I mean, that's basically what we have. We have a domain on the ground, right? We've got a bottom of our solid and a top of our solid. The top of our solid we call the f function, f of x, y. The bottom of the solid we call that the g of x, y. And then the domain d is our either type 1 or type 2 on the ground. So whenever we want to find the volume of that, all we do is we take the top surface, subtract the bottom surface, top minus bottom, but we do it the double integral over that d. So for us, the top here, like we just said, the top, right, this right here is our f of x, y, and this right here is our g of x, y. Right? That's the top of our solid. This is the bottom of our solid. And here's our type 1 region on the ground. So I can set this double integral up, I think. It should be the integral from 0 to 1, then integral from x to 1, and then we're going to integrate x squared plus 3y squared minus 0. I don't need to put that, okay? I'm just, again, trying to stress the formula. So this is f of x, y minus g of x, y, and then d, what is, the inside one is our restrictions on y, so y comes first. Outer integral will be the restrictions on x, so dx. Now in the previous example that we had trouble, Wolfram had trouble with that one, right? Or it didn't have trouble, but we wouldn't have been able to do it, right? We switched the order of integration by looking at the type, instead of as a type 1, we did type 2. Do you think we need that here? No, probably, I mean, look at this. You should be able to integrate this, right? The antiderivative of this with respect to y, that would be x squared y. And then this one would be y cubed. That's it. And then you plug in your two limits of integration, then you should be, it's polynomial stuff, so it should go pretty straight. Yes? So I leave to you, right? The important part is the setup, right? You got to get the setup right. Now, to just show you visually with the computer what this was, here's that region on the ground. Here's the paraboloid, right? There it is. Here's the cutting of the planes. These are all the different planes. And you can see it starts to look pretty, I mean, it's hard to see where that solid is in here, right? I mean, even if you have the ability to graph all this stuff, right? It doesn't help you, I mean, it doesn't solve all your problems, right? To have that doesn't solve all your problems. You still have to figure out where it is. Yes?
Are we integrating the z domain?
Are we, no, no, well, no. You mean this last thing I did here? We're not, but when we do triple integrals, which is the next natural thing to come, this will become the limits of integration on our triple integral.
Or was that not the function that we were integrating?
The f of x was the one on top, the g was on the bottom. I'm not sure what you're asking.
Isn't that the domain?
That's the domain of z, yes. So what I'm saying is, okay, this is actually a really important idea to make sure we all get. See, what we're doing is we're saying, look at this, right? We're saying here's our two-dimensional domain, and we're saying at every point here, it comes out and up somewhere to the surface, right? At every point, it comes out, up to the surface, out, up to the surface. And if you do all of those, you get a solid here. We're finding the volume of that, right? So you first say, okay, give me the restriction on x between two constants. Give me the restriction on y, okay, it gives between two functions of x, right? And then you take all those points, you plug them into a third function, and you get your solid, yes? In triple integrals, we're getting ahead of ourselves, but in triple integrals, what you do is you say, okay, your x's are between two constants, your y's are between two functions of x, your z's are between two functions of x and y, right? And you're taking all the points that live in that solid, and you're plugging it into a function that's in the next dimension up. And that gives you a numerical value. Like do y'all see us? Let me get all this shit out here. I'm getting ahead of myself, I'm sorry, but you asked. So let me get all these planes out of here. Wait, there they go. If I take all those things out, right? Here's the solid that we found the volume of. Okay? What I'm saying is with a triple integral, what we're going to do is this solid now becomes the domain of another function that requires three inputs, x, y, and z. So if I take a point here, I plug it into some function, it spits out a number. Then I take every point in here and plug them into this function that you can't see, and it spits out numerical values for each one. Add all those values up, and it gives you the volume of this hypersolid that we can't see. We call it a hypersolid. It's like in another dimension. So we have a triple integral. It'll be first the restrictions on x, then the restrictions on y, then the restrictions on x and y, and then you go to that, you get the numerical answer. Yes?
So what's the meaning of the volume of that hypersolid?
So like if you say something like, I mean, this, I don't know how applicable this would be, but I don't want to get, yeah, I don't want to go. So just take the Earth, right? And then imagine you could take the temperature at every point inside the Earth. Just imagine you could, right? Then if you wanted to know the sum of all the temperatures, which wouldn't mean anything, right? Like, who cares about that? But the idea is that you have temperatures at each point. If you wanted to add up all the temperatures, you would use a triple integral. The triple integral would basically take every point in this solid